Hello, and welcome to today's webinar, Designing the Future, Signal Simulation for Expanding GNSS, brought to you by GPS World and Platinum sponsor Hemisphere. I'm Bethany Chambers from North Coast Media, publisher of GPS World magazine, and I will be your event manager. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. The recording will be available 2 weeks from today on our website at gpsworld.com/webinars. A link to the on-demand recording will also be emailed to you when it is available. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice in the lower left-hand corner of your console that there is a Submit button. We encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left, then click Submit to place your question in queue. Questions that were submitted during registration may be covered in this webinar. Some questions may also be answered in an upcoming issue of GPS World magazine or in one of our e-newsletters. We strive to answer as many of your questions as possible. Finally, if you experience any technical difficulties during today's event, please select Help to submit your issue, and assistant producer Rick Aldrich or I will personally assist you. Now I'd like to turn today's event over to our moderator, GPS World editor and publisher, Alan Cameron.
Thanks, Bethany, and hi, everyone. Thanks for joining us. This is becoming an annual tradition or an annual feature at GPS World. May is a month that we focus on signal simulation. It's a key topic in the development of all GNSS products. And while we feature it periodically throughout the year and try to have some content in many issues, in May we really bring a spotlight on it. If you haven't already seen the May issue of the print magazine, also available as a digital edition on the website, you'll find that it is filled with signal simulation content and a valuable resource. Part of the May presentation on signal simulation is this webinar, of course. And before I introduce the speakers, I'd like to again acknowledge our sponsor, Hemisphere GNSS, for its year-long sponsorship of this webinar series. Today we have representatives from 5 signal simulation companies, all speaking on the challenges at the frontiers of product design. One of the big challenges in product design these days in GNSS is trying to predict the future and simulate signals that we may not have with us just yet, but are certainly on the horizon. And each of them will address this topic in various ways. We have Steve Hickling from Spirent, John Fischer from Spectracom, Markus Lörner from Rohde Schwarz, Mark Sampson from RaceLogic, and Mark Wilson from IfEN. Some of these gentlemen are assisted by colleagues from their companies, so you may hear more than just their voices. Each of them will speak for about 7 or 8 minutes, and then we'll have a question and answer session with questions submitted by you, the audience, either beforehand when you registered or during the webinar itself. If you have questions, feel free to write them in and submit them, and we'll try to get to as many as we can. Thanks again for joining us, and I'd like to turn the podium over to Steve Hickling now from Spirent. Steve, it's all yours.
Great. Well, thank you very much, Alan, and pleased and honored, as it were, to be the first to go and set the scene. I'm joined by John Pottle, who will be available during the Q&A session. And as Alan had said, the title of our talk is Testing the Future of Navigation and Positioning. Before we come on to the future, just a couple of words for those of you that don't know the history of Spirent. We've been producing simulators for some time, in fact, since before a full operational capability of GPS. And I've got customers in many different sectors and application areas. And our simulators are highly trusted by those users. And indeed, if there's something odd going on the simulator, you can guarantee that that is something that would be replicated in real life. And when we're looking towards the future, and we're representing signals which are not yet available as signals in space, that ability to trust the signals being an accurate representation is obviously a very key and important thing. So a few words, first of all, about the satellite systems that are up there. And now is a time of significant change. Change has not always been very fast in the GNSS space, but really now there is an accelerating pace of change with new systems, signals, frequencies coming on stream, and of course new applications being developed on those, all of which require their own peculiar test needs. So very quickly, we have not only new systems coming in such as BeiDou, Galileo coming up to speed, but also new signals on existing systems. So GPS adding the civil signals on L1C and L2C, L5, and then of course modernization for those using the military codes. And as well as those global systems, there are the regional systems now that are available in many parts of the world. The quasi-zenith system from Japan, ERNS in India, and CAPS in China. One of the points that I would make is that even if these signals are not tracked, all of these signals are going to be there in the environment in which your receivers are working. And so they need to be represented to some extent in your test system. Okay, so this is what it starts to look like with a lot of signals in the RF space. And of course, one of the big advantages of these many signals is improved availability. So more satellites, better coverage, that's inevitably a good thing, isn't it? Well, not entirely. More signals start to introduce noise. The noise floor has actually risen as a result of all these signals in and around the L1 frequencies. And not only that, but whilst there is increased availability because there's more satellites, there's not always improved DOP. So whilst the dilution of precision can be better because satellites are more likely to be placed conveniently around the sky, of course if there's an obscuration problem and you can only see a little bit of sky, having more satellites in that place does not necessarily always help your accuracy. And again, on integrity, there's the potential for using the multiple constellations to assist in integrity, checking one against the other, as it were. But really, it's when you start looking at multiple constellations being used that things really start to get interesting. For example, is your receiver going to make independent calculation of the atmospheric effects based on the navigation data and the model information that's being provided by the various satellites? Or is it just going to use, for example, the GPS model, the Klobuchar model, and ignore the NEQUIC model that's being downloaded by Galileo? Or is it going to use these two models to be able to cross-check and use that for integrity? So there's lots of opportunities that are presented by multiple constellations that the developer will need to test and explore. So from a test perspective, you can't deal with all the signals individually. You really have to be looking at how your receiver is using those signals and making sure that they're accurately represented in the test signal of the test setup of your choice. So how to choose amongst all these signals and constellations? And this is a question primarily for a system designer to select which signals he's going to use, but also the same question is echoed very much in the test regime as well. So what exactly is the system to be used for? How should it be optimized? Would more frequencies or more constellations assist? And what about power consumption? The more signals, the more satellites that are available, the more often a receiver is going to be acquiring. And it's during acquisition that most battery is used. So the choices you make fundamentally affect the performance. And trade-offs affect not only the system design, but also the test design as well. So how to choose the test equipment? Well, clearly this will depend on the type of testing you're doing, but there are a number of things to consider. On the simulation side, the signal iteration rates, whether you have very fast motion to consider, is going to be one of your prime considerations. But motion sources are important as well. Are you going to use built-in motion models, remote motion from a file, such as a log perhaps, or remote motion from another system in real time, like hardware in the loop? And in some systems, motion cannot be arbitrary. It may be, for example, that you're testing a car based on automotive receiver that is using snap to road to improve the accuracy. So having arbitrary motion, figures of 8, circles and so forth, aren't going to be useful. And so the ability to import motion from a map such as Google Maps is quite important, and something that the SimRoute tool that Spirent offers does. And is your GNSS standalone, or is it being combined with other signals? And ensuring then that those other signals are coherent and use the same motion as that which is being used to generate the GPS or GNSS RF. In record and playback, the considerations really are which GNSSs are represented and which other sensors you want to record alongside them. Obviously, live sky will be an accurate representation of live sky, so the inter-constellation biases are not so much of an issue. That's already captured. But you do have to consider how much of a constraint only being able to use historical data is, and clearly on this topic of looking to future constellations and signals that are not yet in space, record and playback has some serious drawbacks. Another thought to consider is around vulnerability, fidelity and integrity. Really what I'm talking about here is noise, whether intentional or unintentional, but also spoofing. Receivers will have to become more fussy, if you like, about the signals they work with. As spoofing becomes more of a threat and the signals that receivers accept will have to have some sort of authentication, they need to be accurate. And so high fidelity becomes a very important characteristic of the simulator. In fact, more important than many other of the features. It's imperative that the signals being reproduced by the simulator are exactly the same as those that a system would see in real life. So if it seems to work okay, but then your receiver stops working, say on upgrade of up issue of the firmware, you need to be satisfied that that's an issue with the firmware and not an issue with an incomplete simulation. So in summary, and mindful of the fact that we've only got a few minutes each, I would point out and re-emphasize that the performance of a GNSS device is characterized by only a few key measures, but they are dependent on a large number of variables. In live sky testing, of course, these are completely uncontrolled. But the object with simulator testing is to be able to control those variables that are going to affect the performance, which is important to you. And the relevance for a particular parameter is very much dependent on the application. So for production test, you're likely to be looking for different things than, say, vendor selection or certifying against a standard. So be sure to understand what you're trying to achieve in your test and design the test to do that specific job. And finally, and again, repetition of what I've said before, fidelity is very important. Just because your particular receiver may not use a feature or a signal doesn't mean to say that it shouldn't be accurately represented in your simulation. Accurate code and carrier phase control is not an esoteric thing, but underpins an accurate simulation and therefore gives you a test that you can rely on. Alan, that's it from me.
All right, thank you, Steve. Thanks very much. And one of the key points that I got out of your presentation is that even if you're testing a receiver, say an L1 receiver, a consumer-grade receiver, you may say, well, why should I worry about BeiDou? My product is not going to use that signal at all. Well, your product will be functioning in an environment where that signal is present. So even if testing an L1 only receiver, you need to have a testing environment that effectively replicates and predicts all the signals. So you may need more than you think you do. We'll turn now to a presentation from Spectracom given by John Fischer. John?
Thank you, Alan. I'm here today to tell you folks about some ways we think we can help you meet the challenges of testing today's modern navigation equipment. So first, I'd like to just give you a word about Spectracom. You may have not heard of Spectracom, but we're a leading provider of global navigation satellite signal management solutions. We do this for the military, aerospace, and high-end commercial applications. And I guess the simple way to think of it is we don't make receivers, but we make a lot of the equipment that goes around receivers. We make precision time and frequency references, interference detection, mitigation solutions, and also simulation and test equipment, which is what I'm here to talk to you about today. So I'll go on to the next slide here, and I'm going to show you three common testing applications, starting with one that is a particularly hot topic today, is spoofing and interference and jamming testing. So I'll start with, in the simulation world, we talk about channels, and a channel can be used to simulate the satellite signal or an interference signal, a jammer, maybe a multipath signal. One of these possible signals that you want to simulate. So we you look at how many channels you're going to need. Is it 16, 32, 64, or even more? In the diagram here, I show how you can take multiple simulators and synchronize them together to give you more capability. And in fact, the one example where this comes in very handy is in spoofing simulation. You can take one simulator and it can simulate the true constellation, and then the other synchronized unit can then be the spoofer. And now, a spoofer is a term we use of it's a bad guy that's trying to fool you with a false signal and maybe pull you off from your navigation. So it's an important thing to test. It's important to test jamming and interference and adding these things in there. So one way you can do it is by connecting, synchronizing units together. The diagram here shows 4 units. There's no real limit. It doesn't have to be. You can use 1, 2, or more units and do this kind of testing. All right, I will then go on to the next application, which is testing for multi-frequency, multi-constellations. I think in the last presentation you saw a nice picture of how complex these signals can be. You know, there's now these. It's more than just GPS. It's sometimes we refer to them as the big 4 now that we're dealing with, and there's a myriad of different signals coming out of all of these different satellites. There was a lot of global cooperation to make sure that there wasn't interference. mutual interference there, that the signals were spaced closely together so that they'd interoperate, but not too closely so that they would interfere. But it can get fairly complex, and so we just like to offer a way of thinking about it. Is if you group all these signals can be kind of grouped into 4 different frequency bands. So if then you look at it this way, you say I have 4 different constellations and 4 different frequency bands, and I have to deal with all these signals. And as was said before, even though some of these are off in the future, like the BeiDou system and even Galileo, they are coming. They are real. They are going to be coming, and you will need to deal with them. Maybe not today, but someday. And so you want to consider that you're going to be dealing in these 4 frequency bands, that you're going to want to maybe establish your hardware to deal with those bands, and if you're setting up test equipment and making an investment in that, make sure you're future-proofing to be able to work with these signals and these frequencies as you go in the future. So I'll go on to the third application, is record and playback. And that was also mentioned before, and you probably will hear more about it in today's webinar. We take a different approach on this, and it offers some advantages of doing it differently. Instead of, and record and playback is, again, something that you do when you're trying to test the environment, test what a particular environment and how your receiver may behave in that environment. So you would go out, maybe do like a drive test, record the signal, and then play it back in your lab so you can then control things. Well, a different approach on that is when you go to do the drive test, instead of recording directly the RF signal, record instead, use the receiver, your receiver of interest, and record that receiver's response to that environment, capturing the NMEA output to a file, that have those parameters include the power levels that's being seen, so that you will see the masking effects from buildings and terrain and things that might be blocking the satellite signals or lowering their reception. So you record that, save it to file, and then upload that file into the simulator and play it back. So now the advantages of that, again, noting that there's a disadvantage that you don't have the true RF, you only have the behavior of that particular receiver in that environment, but you can then modify the playback. You could add interference. You could add additional fading, additional multipath. You could even simulate satellites that are not yet launched, and saying that, okay, doing some what-if scenarios, that what if on this same route now, because next year I'm going to have more satellites, how would this behavior, how would my system work under that? So it has some of those advantages, and it's a different way of looking at record playback, and thought you'd like to consider that. So those are our 3 applications. I guess if I were to summarize, as you might expect, our line of simulators will do all those three test applications, as well as many others. And the fact that we think that these simulators are very powerful, affordable, and easy to use. In the fact that the power, as I mentioned, it's important to have multiple channels, multiple frequencies, handle all the new constellations that are coming down, but also do it very accurately and be able to control things very accurately. And the other thing is also it's important to be easy to use. You do not have to be a navigation scientist to use this. You can generate scenarios using Google Maps and quickly do road tests and operate this thing through a web interface and very quickly create the scenarios you need or use many of the versatile existing scenarios that are available. So I think I've used up all my time. I want to thank you all for listening. I hope you found that helpful. I'll look forward to your questions later. And Alan, I'll turn it back to you.
All right. Thanks very much, John. I want to encourage everyone, as John said, he's looking forward to questions, to use the question feature on your console to submit questions for our speakers, and we'll get to them after we've heard from all five. We'll go now to Markus Lörner from Rohde Schwarz. Markus, take it away.
Thank you, Alan, and welcome everyone. I have the honor now also to give you a quick introduction about what we can do for you and simplify your life in working on your GNSS receivers. Well, there are a whole bunch of different receivers and different applications, as you can see already on the right side of the starting page. So there are a lot of different applications, and pretty much all of them need their own kind of a little bit of look after. But at first I want to give you a quick idea about who is Rohde Schwarz. Well, Rohde Schwarz is really one of the worldwide leading companies working on any test and measurement equipment for wireless communications, including all the location-based services, including GNSS simulators and so on. But we do a lot of more things, like including transmitters for televisions, air traffic control, secure communications. An important thing really also is that we have a global presence, and global presence means service and support, on-site support in a whole bunch of countries all over the globe. So we are there for you and can help you on-site. Well, let's have a look on what we're going to talk here a little bit more in detail. We heard so far that a lot of different standards are coming and more are supported by the different GNSS devices, but kind of common to all of these, there are a whole bunch of different real-world effects, and which of those have quite a lot of an influence on your receiver capability and accuracy. I want to give here a quick overview about those. Well, on one side you can have any kind of issues on the satellites already, like any kind of signal distortion or unpredictable clock behavior. On the signal traveling from the satellite down to the receiver, you can have path delays, which is a common thing surely, and then also scintillation might happen, a really rare thing. The troposphere certainly has its influences based upon where you are about the time and whatever. And then especially in the environment of where you are with your GNSS receiver, there can be a lot of different things. So, for example, like any kind of obscuration or reflections, which then lead to multipath from buildings around you. Any signal obstructions, like if it's traveling through a tree or whatever. Any antenna characteristics. Typically, your receiver, you try to make it an ideal antenna, but it has some effects there, and then depending on where it's mounted, like if it's, let's say, in a rough estimation, if you're having a GNSS receiver in a smartphone and you're sitting inside of a car, there's a lot of things around you which shade off the signals, and last but not least, there can be any kind of jamming or interference. As you can see, there are different colors used on this slide, and the reason pretty much is simple, because all those which are blue can be easily supported within our product. Going a little bit further into detail, for multipath simulation, definitely you want to do all the multipath simulation separately for any satellite. You do not want to just take any kind of an RF fader or so, just to add over the complete GNSS signal, but every satellite needs to be looked up individually. Surely you can set this up for any satellite. Well, that's kind of a starting point, but wouldn't it be nice to just define an environment which you can put the receiver into it, or where you probably want to drive through a city? Well, that is exactly what is offered together with what we call automatic multipath. So you can kind of define any kind of a surrounding and let your receiver go through it, and the simulator automatically takes care about which satellites are being seen, which are reflected, of which you get a line of sight plus a reflection, the amount of delay, the effect of the reflection based upon which material it is, and so on. So there's a lot of things which you probably want to take care of in a real-world scenario, and in the end, you just want to define the environment and let the simulator do its job for you to do the right simulation here. So how do we get any kind of a variation of obstacles for a movement? Well, it's kind of easy to just generate a scenario for a static receiver, like if you just put yourself right inside of a big city. But how does it happen if you want to simulate, let's say, drive around the block in a huge city with a lot of buildings, like through the streets of New York City? Well, in this environment here within our simulator, you can easily just define or even use a predefined city block, driving around the city block with the interactions of the buildings on the right and left side, on the front, and so on. And you can really kind of define your own movement through such an environment. Well, I mentioned in the beginning quickly that, well, there can be an antenna effect, like if you have an antenna which has a better reception in one area than another one, that might be one side, but also if you mount the antenna to a certain car or any vehicle, which could be any kind of a jet or so, or if you are using a receiver like a GPS device in a phone inside of a car, the car has a lot of shielding around you, and you probably still want to be able to simulate moving with inner cars through a city like New York City. Well, then you also need to be able to kind of do the effects to calculate that in. And there is the possibility given for any kind of a different scenario which you can define on your own, but also there are a whole bunch of predefined scenarios given, as you can see on the right side of the slide. Taking it a little bit further, well, there can be a dedicated attitude simulation. Well, if you're not only if you're not only in a car, but for example you have the GNSS receiver on any kind of a plane, on a jet, it can do some rolling, it can add some inclination, and basically you can have some effects based upon the shape of the aircraft, plus also its position in the air, and you want to be able to simulate those with a certain amount of adding the effect of pitch, yaw, and roll, which can be done together with the simulation of the trajectory. Basically, a trajectory can be like a waypoint file, or which could come out of Google Earth, for example, or also use NMEA data. So you can also play anything which a receiver was recording before and take just the NMEA data and apply these for a simulation of a movement together with the automatic simulation of the attitude. To taking it one step further, you might see that, especially in the military world, if you're looking about, well, missiles, for example, you can have, let's say, a certain amount of spinning, like very high spinning rates, and those definitely have an effect. Typically, those missiles have multiple antennas and be able to get always a location fix. Such a thing also wants to be simulated and tested in a certain scenario, which can be fully supported inside of the instrument here. To make it more flexible, hardware in the loop is really an important thing there, because this gives you not only the ability to have predefined waveform trajectories, but really also to be able to change on the fly while the simulation is ongoing which scenario you want to go, which movement you want to see. So this is an important thing also ideally together with any inertial sensor simulation. So if you have a real-world scenario there inside of a any kind of a moving car, for example, or so on. Well, and then you're not only having GNSS signals, so there are a whole bunch of different GNSS standards as we've seen before, but many modern GNSS receiver chipsets, especially in the commercial world, support much more. So there can be mobile comm like LTE, 3G, or so on. And they might have also different interactions to your signal, which you definitely need to test and make sure you still get a good signal quality there. But also you might see some jamming, unwanted jamming from any out-of-band signal, for example, different scenario, different signals, or a wanted jamming, which could be more in a military world where the receiver needs to be able to see what is a real signal and what not. Last but not least, spoofing is an effect which allows a lot of kind of interaction there, and you definitely want to make sure the satellite receiver is able to kind of see what is a real signal and what not. Let me summarize this real quick here for you. Inside of the simulator which we are offering, which does not only support all the different GNSS standards and which is ready for more standards with firmware upgrades in the future, it also supports all the modern communication standards, so it's an ideal platform to be used for multiple use inside with the GNSS, plus also with different interference signals. That being said, let me take it back to Ellen and say thanks to all of you.
All right. Thank you, Markus. We're just a little bit past the halfway point, and we have some questions coming in, so we'll turn to those in a little bit. Right now, we'll go over to Mark Sampson from RaceLogic and LabSat.
Thank you, Alan. Hello, I'm Mark Sampson, the LabSat Product Manager. Thank you for joining this GPS World webinar. In this LabSat section of the webinar, we'll take a few minutes to offer some solutions to your expanding simulation and testing needs. LabSat satellite navigation system simulators are part of the RaceLogic portfolio, which includes the VBox and Video VBox product ranges. VBox or Velocity Box is the name of our high-accuracy GPS and GLONASS data loggers used by our automotive OEM and motorsport customers. RaceLogic has been in business for the last 21 years. LabSat simulators are used by a very diverse range of customers, from mobile phone companies to defense organizations and automotive manufacturers. Here we have a timeline which displays how GNSS constellations have developed over the last decade and how they will continue to grow in the medium term. GPS is established as the standard global system, followed by GLONASS, which became publicly available in May 2007. In December 2012, BeiDou also became publicly available over Asia. The publication of the interface control document allowed us to launch our LabSat 2 upgrade in January 2013. As you can see from this timeline, the next constellation that should become accessible is Galileo, aiming for global coverage by roughly 2016. BeiDou is also aiming for global coverage a little later, by 2020. The next stage of GNSS development will be the modernization phase, which will add further signals to the constellations. As you can see in the timeline, the GPS L2C signal is expected to be available around 2018, followed by the L5 signal around 2021. L1C, designed to increase the interoperability with Galileo, should be available around 2026. These new signals are well into the future. Other constellations have the intention to modernize and develop in a similar fashion. However, it will be interesting to see what actually happens once budgetary aspects come into play. As BeiDou is now officially up and running, LabSat 2 has been made available with the new constellation signal architecture included, adding to the existing GPS, GLONASS and Galileo capabilities. Because recording and replaying live RF signals is a lot simpler than generating satellite data from scratch, LabSat hardware is a lot more cost-effective than the traditional simulators, which need to simultaneously generate signals from multiple satellites in real time. For example, here we are demonstrating the availability of BeiDou, which is inconsistent depending upon your location. As you can see in China, where the system is publicly available for navigation, the coverage is excellent. However, the red trace, taken from the UK, shows only a maximum availability of 4 satellites. The blue trace demonstrates that BeiDou is virtually invisible in the United States. So from a testing and development perspective, how do you validate, test, or develop applications which include the BeiDou signals? This lack of satellite signal availability is exactly what LabSat was designed to counter. Not only does LabSat work indoors in the test lab with recorded signals, it is an ideal system for use with BeiDou-capable product development. With each LabSat 2 system, we provide a number of pre-recorded live scenarios for all of the constellations. Here is a typical setup of a LabSat 2 record and replay system, replaying live recording files into a BeiDou UM220 receiver from Unicor. As you can see, the hard drive, which contains the scenario, is attached to the PC and replaying the raw signals via the LabSat into the device under test, which in this case is the Unicor receiver. As you are no doubt aware, BeiDou is unique as a GNSS constellation in its use of geostationary and orbiting satellites. GPS, for example, only uses orbiting satellites. Here is an example of a recorded single geostationary satellite signal, which shows a comparison of the carrier-to-noise of a live recording and the replayed recorded signal from the LabSat. As you can see, not only is the signal very consistent, which we would expect from a geostationary satellite, but the live and recorded signals are virtually the same. This recording was made on the 9th of April over an 8-hour period in the UK. The average carrier-to-noise for the live signal was 35.99 dB, with the replay average of 35.98 dB. This is a graph of an orbiting BeiDou satellite over a shorter period, 4 hours, and shows that the signal is not as consistent as the geostationary satellite. It also only achieved a 30-degree elevation, and the signal was not as consistent or clear. However, as the graph pattern shows, the recorded and live signals are virtually identical. In fact, the average of the live signal was almost half a dB of the recorded signal. What this demonstrates is the effectiveness in using a LabSat for developing new GNSS devices. With multiple scenarios available, some recorded in ideal conditions, some, for instance, with multipath reflections, or some, as in this case, where the availability of the signals is low overall, a LabSat gives you total realism on the bench and allows for consistent and infinitely repeatable testing. Here is a replay of a recording in China of GPS and BeiDou on the Unicor receiver. As is evident, the PDOP, or overall dilution of position, is 1.42, which indicates that the signals the receiver is using make it a very stable and accurate solution. This is a perfectly acceptable commercial performance. This plot of the same recorded file, with only the GPS signals being replayed, here the PDOP is not as good at 1.95, so you can easily see the enhanced performance of the GPS and BeiDou combination. Finally, some information about the LabSat range. We have a full simulation capability for GPS and GLONASS with our SatGen software, and BeiDou and Galileo signal generation is in development. This gives the user total flexibility, as they don't have to rely only on pre-recorded scenarios and are able to create them from scratch for any location or dynamics should they so desire. However, using a LabSat simply as a record and replay system has its advantages. Recording and replaying RF signals is a lot simpler than generating satellite data from scratch, and LabSat hardware is a lot more cost-effective than traditional simulators, which need to simultaneously generate signals from multiple satellites in real time. If you do need to generate artificial signals, such as simulating a single satellite signal, then the SatGen signal generation software utilizes the power of a PC to create suitable files for playback. We now have various options for GPS, GLONASS, BeiDou, and Galileo. Due to this flexible capability, LabSat is now commonly used by a very wide range of manufacturers when integrating GNSS into their products. I'd like to thank you all for your time, and I'm available to answer any questions that you may have later in the webinar or in the future. Thank you for your time, and goodbye. Back to you, Cameron.
Thanks very much, Mark. As is often the case with such a wealth of material to present and only an hour to do so, we are getting close to the mark, but we have one more speaker, and then we will go over. There's at least one question that I want to answer, so we may perhaps drift over the hour mark. Without any further delay, I want to introduce Mark Wilson from IfEN. Mark, the floor is yours.
Hello, everyone, and thank you all for staying with us through this presentations. I'd like to talk about the practicalities of simulating a realistic test scenario. First, though, just a little bit of background information about IfEN. We've been around for over 15 years, a lot of experience in sort of cutting-edge GNSS technology, and it's really that expertise that we offer within our products. So we have a range of GNSS simulators that provide test solutions for our customers. We also have a GNSS software receiver, which is more for scientific and research applications. IfEN also carry out research and development contracts and can do product customization. The good thing is as well, with that expertise, not only do we provide product, but we provide the technical support to customers to help them in their test programs. One thing, in addition to the IfEN facility in Germany, we've now set up IfEN Incorporated here in California, and that's really to address the needs of the US and American market. So, I guess the challenge we're all facing is the need to sort of make sure our products are comprehensively tested, but at the same time minimizing costs and the timescales involved. And there are various options open to all of us. Each test method had its own advantages and also disadvantages. So, of course, you can go outside and do field testing, which is obviously realistic, but it can be very time-consuming, can be very expensive, and it's relatively limited. You can only do the test at that particular time and date in that location on that specific vehicle. Record and replay. Obviously, you're recording real signals, so it's realistic. There are some limitations on the control. You know, if you want to vary the sort of test parameters, there's not much you can do with that. You sort of record the data. You often don't know what you've actually recorded. You know, you have real signals, line of sight, and you also have multipath and perhaps interference, and sometimes difficult to distinguish exactly what's going on in that environment. There is also a trade-off between the fidelity of the data and the volume of the data that you're going to record. Obviously, when you come to the playback point, you need as much data as you can, but on the other hand, that imposes restrictions on how much you have to actually record in the first place. So with simulation, the nice thing is you have full control of the test environment. You can set any time and date, any geographical location you want, any signals that you want. You know what you've simulated, so you can compare that to the navigation solutions from the receiver. However, some of those scenarios may be considered artificial because you've actually sort of created them. They're not real signals. So what we really need is the possibility of combining the benefits of real data and the control and repeatability of a simulator. So with the comprehensive software features and the flexibility of the IfEN simulator, that really gives us an opportunity here to take recorded data and then use that data to generate a test scenario. So we're not replaying the data, we're using that data to actually generate the simulator files. So that will give you access to the files, and it also gives you the ability to modify the test parameters. The other nice thing about this is that you can, for example, collect data in RINEX format, which means you've got relatively small files compared to the large amount of IF data or digital data you'd have to record for, have to capture for the record and playback units. So there are various steps you go through. One, obviously, you can go out and collect real outdoor data, and the example I have here is for a drive around in a car where data is being captured. The next thing you do is then take that data and prepare the simulation based on the recorded data. Step 3 is to actually run the simulation, log the data. You can analyze the test results, and you also have the opportunity then to extend and expand that simulation scenario. So just going through some of the details of the scenario preparation. Obviously, you have the satellite orbits and navigation data, and that you can use a combination of the precise orbit data that you can get from the web, and then also the broadcast data that you captured in the RINEX files. And obviously, there could be some variation between those two, which is something you might want to test how your receiver deals with that. Next step is to generate the trajectory of your vehicle. And that's obtained by using the recorded data and the software tools provided with the simulator. As you can see in the diagram, we have the route that the car is driven in the test drive, and that's being replicated on the simulator. Next thing then, of course, is to generate the realistic propagation effects through the atmosphere. And again, that's done using the RINEX navigation data. Then finally, you can look at the environmental effects, so things like obscuration and attenuation of the signals. And again, you're using recorded data and the software tools that are provided to generate a power level file. And then that's used in the simulation. So you then come to actually run the simulation, and you can see in the top diagrams, you have the sky plot, which shows you the satellites that are being simulated. And then on the right-hand side, you have a Google Earth visualization feature that is available with the simulator. And that top diagram nicely shows, if you look on the right-hand side, you'll see the rays from the various satellites that are being simulated. And that's quite an open sort of sky environment, so you're getting clear visibility of 9 satellites at that point. And if you look at the lower diagram, you can see on the right-hand side of the vehicle there's very dense foliage, which is actually obscuring the signals. So you can see that what you anticipated when you were creating the scenario is faithfully being replicated in the test scenario. It's also a nice visualization to see what's going on. Then similar diagrams. In this case, the vehicle is about to enter a tunnel. So on the top, the satellites in the front of the vehicle have been obscured. And then below, you see the vehicle has emerged from the tunnel, but some of the satellites behind the vehicle are still being obscured by the terrain. Obviously, when it's actually inside the tunnel, you're not going to see any signals at all. Okay. So as we were saying, the great thing with the simulator is that you can go on then to enhance the test scenario that you've created. With the IfEN simulator, you can actually have up to 108 channels per chassis and up to 9 different frequencies being simulated, and that's all in one single box. That unit can also be fitted with up to 4 RF outputs. As you can see as well, that we can simulate a range of signals. So, for example, if that initial example was GPS only, you could add Galileo, you could add BeiDou, you could add GLONASS, and also the augmentation signals as well, SBAS and QZSS. You could also go on to modify antenna characteristics on the vehicle. You could simulate system failures for things like rain testing. And then the other options there, you could also include, like been mentioned before, things like interference or even false signals or spoofing, just to include that in the test scenario. Okay, so that's obviously a very brief overview. We'd be happy to provide live demonstrations if anyone's interested. You can either contact me directly here in California or visit the IfEN website, and we'd be pleased to provide any additional information and answer any questions anyone would like. Okay, thank you all very much for your time, and I'll hand it back to Alan.
All right, thanks very much, Mark. We do have time for one or perhaps two questions. Here's one that's come in from the audience, and I'll just throw it open to the whole panel. Just jump in with whatever response you have. One of our listeners asks, does the complexity of the simulation scenario, for example, multipath based on building models, jamming or interference, high versus low user dynamics, does the complexity of the simulation scenario affect the simulation in terms of time to pre-compute the simulation, maximum length of simulation, and so on? Floor is open to anyone who wants to answer that.
Okay, this is Markus with Rohde Schwarz. Well, I can only speak now for our simulator, which does the simulation including all those effects in real time. Thus being said, there is no real limitation based upon those scenarios. Well, depending on how long you define the scenario, it may be repeating over time, but in the end there is no limitation with regards to how long does it take to calculate it ahead of time, because there is no calculation time, or how long can the simulation last.
And that
yes,
is Mark Wilson from IfEN. If I can add, a similar situation with the IfEN simulator. One thing maybe to point out is that certainly with the IfEN simulator, when you're creating a multipath signal, you're actually consuming one of the channels on the simulator. So obviously with the IfEN simulator, where you can have up to 108 channels, there's scope there for quite extensive multipath simulation. Obviously, the more complex the simulation, there are various tools to facilitate that, but it will take more time, but we'd be happy to provide technical assistance to anyone who wanted to create a specific scenario as well.
This is John Fischer from Spectracom.
Okay.
Sorry. I'm sorry. Go ahead, please. You go ahead.
Okay, I was just going to say to echo really what Mark and Markus have said on the actual preparation of the scenario itself with the Spirent. It's very similar. It's in real time. There is no pre-compute, and so the complexity doesn't really have any impact on the duration on that, and there is no pre-compute time. What I would suggest, though, to the questioner is that they ask themselves why they want that degree of complexity. And certainly our experience has been that it's quite useful to be able to add impairments one at a time and build up to a very complex scenario. And the reason is it makes it much easier to interpret the results and to actually find out where the impairments are coming in. So if you throw everything into the simulation right off the bat, it can be sometimes tricky to understand what's going on. And indeed, you could get yourself into a situation where you're simulating something a little unrealistic. So our advice generally, whilst there's no penalty in terms of the simulator performance by throwing all these things in, is to start to add these impairments one at a time in a little bit of a more cautious way. So that's not a simulator limitation. That's really just a advice, if you like, from a test methods perspective.
This is Mark Sampson from LabSat. I'd just like to make a point with the LabSat has the advantage of recording real live simulations. And whilst the complexity of the recording will be the same because it's a live recording, we have the advantage of being able to record a video at the same time of the driven route, so that you can see the environment as you're replaying the live GNSS replay and see the two side by side. And the big advantage of The real recording that LabSat does is, of course, that none of the effects are modeled. So this is what the product is likely to receive out in the real world.
And for Spectracom, I guess I would add ours is very similar to the other simulators. We do things in parallel processing, so there's the level of complexity does not affect how long the simulation can be or how much pre-calculation has to be. Things are done on a channel basis, so if you have more channels for more signals, it's all done in parallel.
Thank you, gentlemen. We're going to run just a couple of minutes over because there's one more question that I'd like to get to. I anticipate we'll wind this up within 5 or 6 minutes. Here's a second question for the panel from the audience. Do record and playback systems also provide the capability for a user to generate their own sampled signal, for example, from software, and then to use the hardware to upconvert and broadcast?
As LabSat is a record and replay device, I thought I'd jump in quickly just to say that we do provide software that goes alongside the receiver, which enables you to recreate artificial, we would call them, signals, so that you can simulate any dynamics, any location throughout the globe. And there's a huge advantage to use of a competitively priced LabSat because you can actually create test scenarios on the other side of the world.
For the Spirent record and playback system, the signal format as recorded, so the data format is published, so we can share that with the user, and if they want to generate a file synthetically and then play it back as if it were recorded, that can be done. So we don't make any secret of the file format to our users. That's just there in the user manual.
Anyone else for that particular question?
Similar comment also from Rohde Schwarz. We have not only the GNSS simulator on which I was highlighting, but we also offer an ability to do a record replay where we have customers doing their own scenario simulation and just play it out of the long deep memory of the arbitrary waveform generator inside of it, basically.
Anyone else on that question? All right. I want to thank all of our speakers, and you'll see briefly their emails up there on your screen for Steve, John, Marcus, Mark, and Mark. We will follow up with some printed and or email newsletter form of answering questions that we weren't able to get to in the webinar. Look for my GNSS Design and Test newsletter either later this month or the following month. And I want to thank all the audience for attending. It's been an enlightening as well as innovative seminar. And I want to thank also Hemisphere GNSS for enabling us to bring this information to you. This concludes the webinar. I'll turn it back to Bethany for the official sign-off.
Thank you for attending today's webinar, Designing the Future Signal Simulation for Expanding GNSS. Please be sure to visit gpsworld.com/webinars to find out more about our upcoming webinar, which will be held on June 20th, and also to get a recording of today's event, which will be posted 2 weeks from today. Thank you again, and have a nice afternoon.